Hello Great House. In this video, we will be looking at the 7 theorems under Euclidean geometry. These theorems are important and you may be asked to prove one of the 7 in paper 2. So let us look at the first theorem. Okay, this theorem is about drawing a line from the center of the circle that is perpendicular to a chord, and the intention now becomes, how can we prove that this line bisects the chord? In other words, this line OC from the center, it is perpendicular to the chord AB. We need to show or prove that AC is equal to CB. Right. What is the technique of the proof? You need to produce two triangles, prove that they're congruent, and from the condition of congruency, you may conclude that you have obviously your corresponding sides being equal. In this case, we want to prove that AC is equal to CB. So how will the triangles look like? Let us create them. It is actually drawing radius lines. That and that line segment is called your radius. Okay? And this is our two triangles. What do we know? AO will be equal to OB. CO is a common side. And that angle there is 90 degrees. What will be the angle in this triangle? It's obvious. It's also what? 90 degrees. Okay. Have we met the conditions for RHS? Yes. So by RHS, the condition for congruency, these two triangles are congruent. Okay, and therefore we can conclude that AC is equal to CB. So what are we required to prove? We're required to prove that AC is equal to CB. The construction must always be there, and you can indicate it in the sketch or in words. But I advise that you use the sketch because that is your visual aid, and you must have your sketch supporting your proof definitely. So the proof, okay, in triangle AOC and triangle BOC, what is happening? AO is equal to BO. So by construction, we have radii, okay, and then CO is common, okay, that's a line from center, and we know that angle OCA is equal to angle OCB. Both are equal to 90 degrees. That was given from the information provided before we constructed. Okay, so we leave it there. It's a given information item. So are these two triangles congruent now? Yes, by RHS, right? So therefore, triangle AOC is congruent. Remember, 3 lines there for congruence, not 2, right? And triangle AOC is congruent to triangle BOC by right angle, hypotenuse, and one side has been shown to be equal there. So therefore, we have the equality of the two sides. AC is equal to CB. Why? Because triangle AOC is congruent to triangle BOC. And that's where you leave it. Okay. Let's go to theorem 2. Okay, in this theorem, we are given an arrowhead and we are asked to prove that this angle at center is twice this angle at the circumference. So how do we go about it? What is the technique? Technique here is to create a radius. Okay. How? Like this. We just join A and O, and that becomes your radius. And you can clearly see that that is a radius, that is a radius, and that is a radius. So I prefer even indicating with that letter R to just make sure that I see what is happening in the diagram. Okay, so once you've created a radius line, you have done what? Produced two triangles in the process. And you want to now work in these two triangles in such a way that you will end up with an expression for this angle, which will be 2 times the expression of that angle. Okay, you can introduce numbers, notation, symbols that will help you do that. Okay, so I'm gonna let this angle be x and that side let that angle be y. We cannot say x and x and just directly assume that they're equal, or y and y. Okay, it needs to be a proof that applies in any context, and it is a general convincing statement that you're giving and not for specific purposes or values. Okay, so what type of triangles have we produced? Isosceles triangles, and we understand that the base angles will be equal, so that will be x. Base angles will be equal, so that will be y. Okay, what can we say about this guy? Angle BOA. So this angle here will be 180 degrees minus 2x. What can you say about that angle there? That side, this guy will be 180 degrees minus 2y. Okay, and we will later talk about the revolution or angles around the point. So that is the essence of the proof. So let's go for it. Okay, construction is indicated there. We don't have to write it in words. Okay, so we said let angle BAO equal to x and angle CAO equal to y. Okay, so by this condition, we know that angle BAO will be equal to angle ABO, both of them being equal to x, because these are angles opposite equal sides. And we also know that angle ACO will be equal to angle CAO, and they are both equal to y, because these are angles opposite equal sides. Okay, so then we come to the center. Okay, angle AOB. Angle AOB is equal to 180 degrees minus 2x, interior angles of a triangle. And we know that angle AOC is equal to 180 degrees minus 2y, again by interior angles of a triangle. Okay. Now to find angle BOC, of which we must talk about in our required to prove statement, we need to show that angle BOC is equal to is 2 times angle A. So by revolution, we know that angle BOC will be 360 minus what? The sum of these two angles. So 180 degrees minus 2x plus 180 degrees minus 2y. Yes? By what? Angles around a point. We can just say a revolution. Now, obviously, this, guys, will fall away, and the distribution of the negative sign will give you 2x plus 2y. And if you factorize the 2 there as your HCF, you end up with 2 into x plus y. Where is x plus y? X plus y is the sum of x and y right there at A, so it represents angle A, and therefore this is equal to 2 times angle A. Are we done? Yes. Okay, you leave it there. Let's go to theorem 3. Now we proceed to theorem 3, which has to do with a cyclic quad. In this case, we must prove that the sum of the interior opposite angles of a cyclic quad, they are what? Supplementary. Okay? What is the technique of the proof? You draw line BO and OD, which is your radius. And by applying the previous theorem, angle at center, you are able to get to the conclusion of this proof. So let's do that. What is this? What is that? They are radius, they are radius. Okay? We have seen that this angle, we're going to call it O1 in this case, is related to that one. It is 2 times angle A. We also have seen that this angle, we're going to call it O2, is related to this angle. Angle O2 will be 2 times angle C. Okay? And then angles around the point is 360. If you have the 2 there and the 360 divide by 2, are you going to get the 180? Yes. So that is the essence of this guy. Okay, we have drawn our radius, and therefore we can talk about the following. Let angle BOD be equal to angle O1 and O2 respectively. Okay, what does this mean? It means BOD is a split angle. Okay, so it is not one angle at this point O. There are actually 2 angles that we are talking about, and then we need to be very specific there because it's a split angle. Okay, so therefore, what can we go to now? We can talk about angle O1 being equal to 2 times angle A, because angle at center is 2 times angle at circumference. And we know that angle O2 is equal to 2 times angle C, because angle at center is equal to 2 times angle at circumference. Okay? What is angle O1 plus angle O2 equal to? 360. Okay? It's angles around the point. By substitution, we have that angle 2 times angle A plus 2 times angle C is equal to what? 360. Division by 2 both sides, we can therefore conclude by saying that the sum of angle A and angle C is equal to 180. Okay, now are we done? Yes. Let's go to the next theorem. Okay, now let's move on to this theorem, the tan-chord theorem. It says that the angle between the tangent and the chord is equal to the angle subtended by the same chord in the alternate segment at the circumference of the circle. All right. Now, what is the technique of the proof? The technique is to draw a diameter so that we can introduce angles in the same segment, and also working with the tangent perpendicular to the radius relationship, we can arrive at the conclusion of our proof. Okay? In this diagram, we actually have two choices or two roads that we can follow to prove these theorems. Either working with this angle here at this side between the tangent and the chord, or this angle that side between the tangent and the chord. And obviously it will correspond to different angles at the circumference. So if you choose this angle right here, chord KL subtends angle P. So you need to prove that it is equal to angle P. If you had chosen this angle, then you would need to prove that it is equal to angle K. So for enrichment, try that after watching this video. Okay, so let's go for it. Here is our construction. Diameter there. Okay, and then we link it to the chord KL that subtends this angle that we're working with. Okay, let me just fix it there. It should be a straight line. Okay, what do we know about that angle? It's 90 degrees, angle in a semicircle, and that is a radius, and a radius meeting a tangent at the point of contact. Angle of the angle formed there between the tangent and the radius is 90 degrees as well. Okay, so we're required to prove that angle SLK is equal to angle P. So let us start. So we have formed our diameter here, and we can give this point a label. Let's say it's J, and we connect K and J with a line segment there, a chord as well. Okay, so what do we know? We know that angle SLO is equal to 90 degrees because a tangent is perpendicular to a radius. Okay, so therefore angle SLK will be equal to 90 degrees minus what? KLJ. Right? Now we know that angle JKL is equal to 90 degrees. Why? Angle in a semicircle. Okay, but angle J is equal to angle P. Angle J is equal to angle P. Angles in the same segment. Okay, so then we need to find the expression here for J. Okay, and this will be what? We know that in this triangle KLJ, there's 90 degrees already. So this will be 90 degrees minus that angle there. So it will be 90 degrees minus KLJ. Okay. Is it equal to that? Yes. And remember, angle J is equal to angle P. So therefore, angle SLK is equal to angle P. And that takes care of the proof for the 10-chord theorem. Good. Let's move on to the next theorem. Okay, we are now proving the proportionality theorem. In this case, we have a triangle where there are two parallel lines, okay? And we need to prove that AD over DB is equal to AE over EC. So in other words, this line divides the other two sides of the triangle proportionally, okay? What is the technique of the proof? We need to work with ratio of areas, and the general formula of an area of a triangle is half times base times the perpendicular height, and that is what we need to construct, perpendicular heights. Okay, so how? We need to say from this vertex E, there's a perpendicular height h, and then from that vertex D, there's a perpendicular height called K. Okay? And we join E and B, and then we also join D and C. Okay. So by the looks of things, we're going to have two triangles that will allow us to talk about this ratio on this side. We're going to have two triangles that will allow us to talk about the ratio on that side of the triangle. What is a common triangle? This one, ADE. Okay, so let us start the proof. Okay, area of triangle ADE over area of triangle DEB is equal to what? This is half times what is the base for ADE? The base is AD. Okay. What is the perpendicular height? It's denoted by H. And this one is half times DEB, DEB. What is the base? It's DB times what is the perpendicular height? It's H. They have a common vertex, ADE and DEB. Okay, so we state that as the reason that allows us to talk about H and H there. Cancellation happens. What is left? AD over DB. We have the left-hand side of the required to prove statement. Let's go to this side. Okay, area of triangle ADE over area of DEC now is equal to half times what is the base? AE, perpendicular height will be K. Half times what is the base? EC, perpendicular height will be K. Common vertex, and therefore the two triangles have the same height, K. Cancel out, you are left with AE over EC. Now, what remains? We need to connect these two ratios and prove that they are equal. Already, the numerators are equal. We just need to show that this area will be equal to that area. Okay, so how can we do that? Therefore, if you look at this triangle right here and that triangle right there, okay, and you take DE as a common base, having a perpendicular dropped from DE, wherever you are, as long as it's a perpendicular line segment, will then constitute your what? Your height. Let's call it L, height L, height L. Okay, so DE is the base and L is the perpendicular height. So these two triangles will have the same area. Okay, by that reasoning. And again, we have parallel lines. Okay, in other words, you will have a perpendicular height throughout the parallel lines, no matter where you are. And therefore, you can conclude like that. Okay, unless the two lines are not parallel, then we were not going to be able to make that mathematical observation. Okay, so therefore, the area of triangle DEB is equal to the area of triangle DEC. Why? Because they have a common base, DE, okay? They have the same height. What causes the same height? It's because DE is parallel to BC, okay? And if you have a perpendicular line between parallel lines, that will be constant throughout. So therefore, we've proven the equality of these two areas of the two triangles, and therefore AD over DB is equal to AE over EC. Are we done? Yes. Let's go to the next theorem. We are now at theorem 6 of 7. This theorem says if two triangles are equiangular, then their corresponding sides are in proportion. So we see it here on the board. There are the two triangles, and we are given that angle K is equal to angle G, angle L is equal to angle H, and angle M is equal to angle I. What are we required to prove? KL over GH is equal to KM over GI. What is the technique of the proof? We need to construct a line inside this triangle that will allow us to connect the angles that form to this triangle, move in the direction of parallel lines so that we can introduce proportionality theorem. Okay, so that is the essence. So what are we going to do? We're going to mark a point here called P and draw a line to the other side and mark a point Q such that KP is equal to GH and KQ is equal to GI. And we can already see that by side angle side condition of congruency, these two triangles will be congruent. Okay, so let us start there. Okay, so we know that in triangle KPQ, and triangle GHI, what is happening? KP is equal to GH. This is by construction. Okay? Angle K is equal to angle G. This is given. And by construction, KQ is equal to GR. And therefore, triangle KPQ is congruent to triangle GHI by side condition for congruency. Okay? So if they are congruent, it implies what? Corresponding angles are equal and corresponding sides are equal. So that angle is equal to that angle, meaning that this angle P will be equal to that angle H, and angle Q will be equal to angle I. Okay, so from this, we can make that statement and say, therefore, angle KPQ is equal to angle H. Why? Because triangle KPQ is congruent to triangle GHI. Okay? But we know that angle H is equal to angle L. This was given. So what can we do now? We can connect angle KPQ to angle L. So therefore, angle KPQ is equal to angle L. So it's dot there, so we're going to put a dot there as well, and we have connected these two angles. So what can you say now? There's a line there, there's a line there. This angle is equal to that angle. What type of angles have formed? Are here corresponding angles. Good. So therefore, PQ is parallel to LM because corresponding angles are equal. All right. So we bring in the parallel lines and we're now moving in the direction of what? Proportionality theorem. KL over GH is equal to KM over GI. That is what we want to do. We're going to bring in these two statements after proportionality. So KL, okay, over KP, we know that KP is equal to GH. And then Km over KQ, we know that KQ is equal to GI. And then we arrive there. Okay, so Km or KL, let's start with that, over Kp is equal to Km over Kq. What allows for that? Line parallel to one side of triangle. Okay? And we now bring in that substitution. KL over what? GH will be equal to Km over GI. And there we go. That is the last line of the proof. Okay? Not complicated. As long as you follow the correct mathematics, you should give a clean proof that will give you full marks. All right. Let us go to our last theorem. All right, we are at our last theorem, and it is similar to the previous theorem. The only difference is that we are starting with sides in proportion and proving that the two triangles are similar. Okay, so here are the two triangles, and we're given that the sides are, or the corresponding sides are in proportion, and we need to prove that the two triangles are similar. Okay, the construction is similar as the one that we have done in the previous theorem. Let us mark a point here called G and draw a line to the other side and mark that point called H, such that AG is equal to DE and AH is equal to DF. All right. So what can we now do? In our proof, obviously, we want to start with what's given and by construction see how we can include that. Okay, so we know that AB over DE is equal to AC over DF. Okay, but what did we say about DE? DE is equal to AG. So this ratio now becomes AB, this is given, AB over AG, which is equal to what? DF is AH, AC over AH. This is by construction. Okay, AB over AG is equal to AC over AH. This condition only applies when this line is parallel to that line. It's called the proportionality theorem. But because we are moving in the reverse direction, it becomes here converse. Good. So therefore, GH is parallel to what? BC. Converse of the prop theorem. Okay. So now, this is what we know. Okay. What type of angles will therefore result? Okay. We will now have this angle equal to that angle, and that angle equal to that angle, and that will be the common angle, meaning that triangle AGH will be similar to triangle ABC. Okay? So, therefore, what do we have? Angle AGH is equal to angle BY, corresponding angles. GH is parallel to BC. Okay, and also we have that AHG is equal to angle C. Okay, meaning that, this is by corresponding angles, and GH being parallel to what? BC. Angle A is common. Therefore, triangle AGH is similar to triangle ABC. Yes? By what condition? Equiangular triangles. So from here, can we introduce proportionality? Yes. Therefore, AG over what? AB is equal to GH over BC, which is equal to AH over AC by similar triangles. Okay, we now want to use substitution to now go to the concluding part of the proof. AG is equal to DE. So we have DE over AB here is equal to GH over BC is equal to AH over AC. All right. And this substitution, you're allowed to make it because of construction. Okay. Now, we want to relate the following. We see that, yes, it's linked to what? That. And why do you want to link it? Because there's a BC here, there's a BC there. But it is written in the inverse direction, or we have swapped the numerator and the denominator. So we can do that and then equate. So it means DE over AB is equal to what? EF over BC, okay? And this will be equal to what? DE over AB is equal to GH over BC, meaning that GH and EF are equal. So 1, 2, 3, 1, 2, 3, okay? So it means these two triangles are what now? Congruent by a side condition of congruency. And in simple terms, congruency means equality. They are the same, right? These two triangles are the same triangle. And therefore, we can come back here and replace triangle AGH with triangle DEF. And if you do that replacement, you will see that triangle DEF is similar to triangle ABC. Is that the statement that you wanted to prove, or we wanted to prove? Yes. So that takes care of this theorem, and it brings us to the end of discussing these different proofs of the 7 theorems. And remember, provide a clean proof, and a proof without a construction will not help you get any marks. That will definitely help you to achieve a 0. You don't want that, okay? So let us ensure that we take care of these proofs and we collect all the marks. It's usually 5 to 6 marks, this type of questions where you're asked to prove one of these theorems. And I believe that after this video and after this video, I know that you are well equipped now to ensure that you get all the marks. Thank you very much for watching this video until the end. I believe that you are a subscriber. If you've not subscribed yet, please subscribe and continue to watch many other videos that are in the playlist and enrich your mathematics. All right. I wish you well. Go out there and be excellent. Sharp, sharp.